Everybody. Today we have our THCP General Club meeting of this week, and today Professor Aulakh will continue his second part of the talk on grand pleromal transmutation, UV condensate via Konishi anomaly, dimensional transmutation, and
Some internet problem. Okay, very good. So let me start. Can you all hear me? Can you hear me?
Yes,
Yeah.
I can hear you.
Okay, so I'm last time I was running through the background contextual material for why this work was done, and the bulk of the journal club meeting in the time allotted of 2 things is going to be taken up with that. And I hope by the end of this meeting to give you the basic idea, and then if anybody is still interested, we can think about any further meeting. So I think the more important thing is to see the context that is motivating an attempt to make a consistent asymptotically strong theory, so that it's clear that it's not just an academic exercise, but is something that is a natural response to the status of a very successful grand unification, even canonical grand unification model, which runs into a difficulty, a fundamental difficulty. And this is a paper that we are talking about is an attempt to resolve that difficulty. So, so we said that there's a chain of unification beginning with the standard model, or even with SU3 cross U1 is a subgroup of the standard model gauge group. And that can be very naturally extended to be or seen to be a subgroup of the left-right symmetric group, where the SU2L is partnered with another SU2, which acts on the right-handed fermions, the right chiral fermions, and the U1 hypercharge attains a much more transparent meaning as the gauging of the B minus L anomaly-free symmetry of the standard model. Okay, so now this guy, you can easily realize that SU4 contains SU3, has obviously got SU3. Any SUN group has SUN minus 1 times U1 as a maximal subgroup. And in fact, if you look at the quantum numbers, because the diagonal generators, the new diagonal generator, SU4 is rank 3 and SU3 is rank 2. So there's a new diagonal generator. And that new diagonal generator, if you take the fundamental representation, which is the fourplet of SU4, the eigenvalues on the diagonal are 1/3 and -1, which are precisely the B minus L eigenvalues of the quark triplet and the lepton triplet, whether left or right, which means that you can embed the one generation of standard model, left-right model fermions, which includes the right-handed neutrino, in a pair of Pathi-Salam representations, which is a doublet under SU2L and a fundamental of SU2R, and another fundamental of SU4, and another fundamental fourplet of SU4 and a doublet of SU2R. So this is very naturally, this guy fits in here and this guy fits in here. So it's as symmetric as you could almost wish for. The next thing that you would like to do would be to put them all together, and we'll see that is the next stage of the unification. So now, as usual, you need something to break the SU4 symmetry down to the SU3 cross B minus L, and that can be done in a very easy way with an adjoint of SU4, which is a singlet under SU2L and SU2R. So at some high scale, much higher than, let's say, or somewhat higher than the right-handed SU2R cross U1 B minus L breaking scale, which we already saw has to be greater than about 4,000 GeV. So that's already much higher than the standard model scale. Then at some higher scale, you would break down SU4 down to these, down to SU3 cross U1. by using the diagonal elements of this omega multiplet. And basically it would be proportional to T15, the generator that I just showed you. It would be proportional to that, and therefore it would commute with color and with B minus L, and therefore these would be the unbroken, the little group of the symmetry breaking would be SU3 cross SU1 B minus L. Now, to identify what Higgs we should use to get fermion masses, we always take the product of the fermion representations, and then the Higgs will lie in the conjugate of those representations. So 4 cross 4 gives you 6 anti-symmetric and 10 symmetric. It turns out that the 10 symmetric contains multiplets which are color singlets and have B minus L is equal to -2. And therefore 10 bar contains singlets with +2. And we already saw that delta L and delta R should contain neutral particles with such properties. So therefore we introduce a delta R, which is a 10 bar of SU2, which is a 10 bar of SU4 and a triplet of SU2. Because obviously since you're taking you're taking the product of 4, 2, 1 with 4, 2, 1. So that will give you a 6 plus a 10 plus a 3. So this 4 times, this FL cross FL will give you 6 plus 10 plus comma 3 plus 1 comma 1. Okay, and similarly for FR. So you need these guys. The delta L and delta R that we use for the right-handed symmetry breaking will now be embedded inside this guy, which is a symmetric representation of SU4. And similarly, you can also, so for giving the quarks a mass, we had a bidoublet 2, 2, 0 in the 1, 2, 2, 0 in the left-right model. This was B minus L, and this was color. This was SU2L, and this was SU2 right. So you can generalize that either to a new guy, which is a singlet of SU4, then obviously it is a singlet of color and B minus L. Somebody's mic is on. Could you please switch off all your mics? The host could please mute the mic. Yeah, thank you. So, or you could use also another representation, which actually I will later on call sigma, and let's call this phi. And such representations would be able to give masses to the thing by, you could put a phi here or a sigma here. So FL bar FR, since phi will transform as U L phi UR dagger under the left-right part, and phi would also transform as U4 phi U4 dagger and U4 dagger under the SU4 part. Therefore, this guy is gauge invariant. And by giving webs to the color and neutral particles inside the phi or the sigma, you could get various quark masses. The Dirac masses of the charged quarks and leptons would come from here. And then, as usual, the Majorana masses for the left and right neutrinos would come from the coupling to the delta R wave, which is very big, or delta L wave, which is very small. Okay, so delta R is very big. So therefore, the seesaw mechanism is the natural thing, both left and right, to operate in this kind of model. You have baryon number violation in this theory. The charge formula is T3L plus T3R plus B minus L by 2 still, but B minus L by 2 is now part of the SU4 gauge group. So if you have charge conserved, then delta Q is 0. And since if you're at high energy, since you want to suppress any baryon violation, then delta T3L should also be 0 in the process. So therefore, you'll get a selection rule that T3R should be equal to minus the change in B minus L. And if you're violating T3R spontaneously with delta R, then delta B minus L will come out to be equal to 2. Okay. Now it turns out that the gauge bosons of SU4 do include leptoquarks Z and Z bar with these funny B minus L quantum numbers, which are combinations of quark and lepton quantum numbers. But because they are conjugate to each other, so you see you have these couplings that the Z couples to a quark and a lepton. That's why it's called a leptoquark. But Z bar then also couples to L bar and Q. So therefore, when you have a diagram like this, the net change in baryon lepton number is 0. So you have no gauge boson mediated baryon violation. However, if you introduce, because you have these scalar leptoquarks which inside the Higgs of various kinds, inside the delta R and delta L and also inside sigma, you can have processes like delta L equal to 0, delta B equal to 2, which are called NN bar oscillations. So a neutron oscillates spontaneously into an anti-neutron. And this kind of diagram with 6 external fermion operators it's a dimension 9 operator, because the dimension of a fermion field is 3/2. So 3/2 times 6 is 9. So therefore, as an amplitude, in the effective Lagrangian, this diagram would show up as something which needs a suppression by 5 powers of the mass. It's proportional to a delta R wave. So this would be the strength of this operator. Okay. What is called the Wilson coefficient or whatever. So now, therefore, this would lead, since the particles outside are D, 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 U, U. Okay, so therefore you'll have essentially the particles of 2 neutrons. So this would lead to a Majorana type mass after, for the neutrons. Neutrons are neutral particles, so they can have Majorana masses, but those Majorana masses would violate baryon number by 2 units. And so therefore the strength of this, and you can deduce what kind of, so such a mass would lead to a oscillation time between the neutrinos, between the neutrons. So the lambda QCD would enter into this thing to make the dimensions right of the operator. Okay, so this has to have dimensions of mass. So therefore, when you write it in terms of neutrons, you would get this lambda QCD to the power 6. Okay, and you can deduce just dimensionally, put in the masses of this as about 10 TeV, and these F's as some generic couplings of the order of 10 to the power of -1, and you would get a neutron anti-neutron oscillation time. You can deduce that, which is greater than about 10 to the power of 7 seconds. And the current limits are about 10 to the power of 9 seconds. So by fiddling with the parameters, you land up more or less near what the current limits are. So there are experiments going on this kind of thing. Both on bound and free neutrons. I think the European spallation source in Sweden is going to check these numbers. It's still an exciting experiment to do. So people are trying to improve the limits. There are also processes in which delta L is equal to minus delta B. The most interesting of them is where a neutron goes to L minus plus pi plus. And that also, by introducing this sigma 15 to 2, you can get amplitudes like that. I won't spend my time on that. So let me go on. So the next stage, next grand unified theory you need to be aware of is that the most popular SU5 gut was introduced. I mean, grand unified theory was introduced shortly after the Pati-Salam theory. And for a long time, it was the unquestioned king of guts, because SU5 is a rank 4 group, which is also the rank of the standard model, since SU3 has rank 2, SU2L has rank 1, and U1 has rank 1. So total rank is 4. So the minimal sort of grand unified theory you might want to build seemed always to be SU5. Why should you make the extra assumption that nature restores parity or restores chirality, left-right symmetry at some low scale? Why should you not just work with the minimal data? And so people always preferred this. It was only the discovery of neutrino mass that turned the tides against SU5. Otherwise, SO10 and left-right models, although they are so beautiful and natural and they answer so many things logically, which SU5 cannot do, was never preferred until about 1998 or 2000. Very few people like to consider SO10 as a grand unified model. So that tide changed with the discovery of neutrino oscillations, which confirmed that neutrinos have mass. So the SU5 gut, however, one must be aware of it. It's also a subgroup. SU5 cross U1 is a maximal subgroup of SO10, so it's worth knowing it even for SO10 people, that you see, both of them have rank 4, and the generators are hypercharged T3 of SU2L and T3 and T8 of color. So the 5-plet, the fundamental of SU5, breaks up into a triplet and a doublet. A triplet of SU3 color and a doublet of SU2 left-handed, the standard model guy, and also it has some hypercharge. If you take the generator T24 of SU5, remember we had it goes as 8, 15, 24, 3, 8, 15, 24, so n squared minus 1. So 5 squared minus 1, that's the new diagonal generator. Right? When you set up the generators, you always do it by repeating the Gell-Mann trick, that you start with Pauli matrices for SU2 with either 1 and 1 on the off diagonal, or iota and minus iota. Then that's in the 1, 2 element for Pauli matrices. Then you use 1, 3 and 2, 3 and so on for SU3, and then for SU4 you have another row and column, so you put 1s or iotas there, and for SU5 you have another row and column, so like that you keep building up the generators. So, but always you'll have also an extra diagonal element, and therefore there'll be an extra diagonal generator, and that's the increase in the rank. So T24 turns out that it has the structure of identity matrix in the color sector and identity matrix in the SU2L sector, and it's traceless like all SU5 generators. So therefore there has to be a normalization constant minus 2/3. Okay, so you can then identify this SU5 quintet, the fundamental, with the D right-handed and L conjugate right-handed, which is the antiparticle of the left-handed doublet, anti-field of the left-handed doublet, and then very nicely the hypercharge, this T24 turns out to be nothing but the hypercharge. Okay, so D right-handed has charge minus 1/3, so 1/2 of minus 2/3 is minus 1/3. And similarly, for this guy, the charges work out right. If E plus has charge plus 1, so that's T3L is plus half, and then hypercharge is 1, so plus half will give you plus 1. And lower one will be neutral. Notice that new conjugate right-handed is related to the left-handed neutrino. New conjugate left-handed is the right-handed neutrino. And moreover, all the other quarks and leptons can be fitted into the 10-plet of SU5, which is an anti-symmetric. 5 times 5 anti-symmetric matrix has 10 independent elements, 5 times 4 by 2. So you can fit one generation of standard model fermions, but no new R. Okay, that's exactly the situation in the original standard model. So you can fit it into 5 bar plus 10 or 5 plus 10, depending on the chiralities that you assign. So if you wanted to use only left-handed fields like you use in supersymmetry, then you would use a 5 bar. So now this guy is also gauge anomaly free. It has no SU5 gauge anomalies. You know, SUN groups have gauge anomalies proportional to the symmetric structure constants DABC. Okay. So if you add up the DABC contributions of these chiral fermions for one generation, you find 0. So that's another nice thing, that the anomaly freedom of gauge anomaly freedom of the standard model also carries over trivially to SU5 once you assign them like this. And the conjugate up quarks, the quark doublet, and the lepton singlet, charged lepton singlet fit neatly into the 10. antisymmetric 10. And these mu nu can be broken up into a color mu bar and a mu hat, as we did in the beginning, which runs over the SU2L and this over SU3. And so everything fits in neatly. So one generation is given by a 5 plus a 10. There's no nu L, nu R. Now since the right-handed neutrino is a gauge singlet, therefore there's no gauge logic that you can apply to the seesaw. I mean, you can put in singlets and you can get some seesaw formula, but there's no gauge constraint on that at all, because the right-handed guy is a singlet. The gauge symmetry breaking is done by using, as always, an adjoint multiplet. So you have a 24 plate of SU5, and that breaks up into 8 generators corresponding to SU or 8 gluons corresponding to. So think of this as being a vector field, and it's a traceless 5 by 5 matrix. So there would be 8 gluons, 3 W bosons, and 1 hypercharged gauge boson, and 2 leptoquarks. Now these leptoquarks are serious guys, because you have 5 and 10 bar. When you exchange these leptoquarks, you can get B violation, okay, which you could not do in the Pati-Salam model. So you can have gauge, and since the renormalization group gives you a handle on the scale of SU5 breaking, therefore you can estimate reliably the baryon violation amplitude. So SU5 gets broken down at some very high scale. We'll see that scale is some 10 to the power of 15 or 14 GeV in non-supersymmetric SU5. So it breaks down to the standard model by the wave of sigma being proportional to the hypercharge generator, which I've written over here. Okay, and all these standard model generators commute with the hypercharge. So therefore, the residual subgroup, gauge subgroup, is just the standard model subgroup. And now you can write down the interactions of the fermions by using the covariant derivative. There is no play in that. Everything comes out straightforwardly. And what I've done here is I've written down the interaction of the leptoquarks with the quarks and leptons. So there would be 2 different kinds of interactions coming from the 5 plate and the 10 plate. Okay, all this stuff is simply, you can look at it later if you like. I have assigned the quantum numbers over here. So you see that the assignments are, so this is X. Okay, so anyway, this is just an unpacking of the gauge interaction. So so B minus L, so this is, I've deduced what the B minus L of X is. So B minus L can be assigned consistently to X and X bar. And it turns out to be conserved accidentally. So any process that happens here will conserve B minus L. And you can now have diagrams where an X and a X particle leptoquark is exchanged, but at the vertices, you have different quarks and leptons. So this gives you an effective operator, a 4 Fermi operator, which violates baryon number by 1 unit and lepton number by 1 unit, but B minus L turns out is not violated. However, B plus L is violated by 2 units. So the lifetime, the rate for this is proportional to the propagator. This is some enormous mass. So therefore you don't have to worry about the momentum that is exchanged. What is important is the mass, and then you have 2 SU5 couplings there. So therefore it has to be proportional to G5 to the power of 4, the rate, divided by mx to the power of 4. And in order to get the dimensions right, then you need 5 powers of the relevant mass, which is the mass of the baryon or the nucleon that is decaying. And so this gives you a lifetime which is proportional to the 4th power of mx. And at the time where this model was invented, the lifetime limit was about 10 to the power 28 years. And that already told you that mx has to be bigger than 10 to the power 15 GeV. So therefore you have immediately a gauge hierarchy problem. How do you separate in a theory with scalars this large scale from the small electroweak scale? And as I said, there's no logic to the seesaw mechanism, and I won't belabor that. It's sort of obvious. So let me go on. So now comes the problem of why do you want to work with supersymmetry? So if you have heavy particles like the X, then and you have this light gauge guide gauge boson W, which gets a mass from the Higgs, which is also therefore has to be light, then the loop corrections to the mass of the Higgs are proportional to the mass squared of this heavy particle. And this is 10 to the power 15 GeV, whereas m Higgs squared or mW squared is 10 to the power 2 GeV. So this is madness. The correction to a mass of the order of 10 to the power 2 GeV is 13 orders of magnitude bigger. Well, okay, 11 orders of magnitude bigger. But the point is, there's some coupling constant here, but this guy is very big, just from the proton lifetime. So that means you have to do some incredible fine tuning of the renormalized coupling order by order in perturbation theory, and people don't like doing that, and it's ugly and inconvenient. So this is called the gauge hierarchy problem. Now supersymmetry gives you a technical fix to this, that it allows you to do the fine tuning once and for all, and after that the supersymmetry will protect this from happening. That means in supersymmetry what you do is, for each particle in your theory, you introduce a superpartner particle which has the opposite statistics. That means if you have a boson, then you'll have a fermionic superpartner, and if you have a fermion, it will have a bosonic superpartner. And it turns out that the supersymmetry algebra and all tell you that for the vector particles you need Majorana partners, which are also in the adjoint representation of the gauge group. And for the quarks, which are fermions, you need scalar particles, which are called, so you put always so these guys are called gauginos. So the partner of the gluon is called gluino, partner of the W boson is called the vino, which is also Italian for a drunkard, and there's the partner of the B gauge boson is called a bino, and similarly Zeno and so on. So now the quarks have scalar partners, and their names are simply given by appending an S to the name. So a quark, you have a squark, and for a lepton, you have a slepton. And for the Higgs, which are scalars, so this is S is equal to 0, you have partners which are S equal to half. And these are chiral fermions, okay? The partners, the quarks here are chiral quarks. So the scalars here are complex scalars, but here this Higgs is a complex scalar. Its partner is a left or chiral fermion. And that means that anomaly freedom means that you cannot make do with just one Higgs. You have to have a partner with the opposite, hypercharge. And that turns out that you have to have a H and a H bar. So the minimal supersymmetric standard model has this, each gauge boson has its partner gaugino, and each quark has its partner squark in each generation, and the Higgs have been doubled. So you have a Higgs and a Higgsino, and a Higgs bar and a Higgsino bar, which has the opposite hypercharge. And this is required by anomaly cancellation, by gauge anomaly cancellation. So now when you calculate the corrections to the propagator of the scalars, then you see that you would have a partner contribution, because you have supersymmetry at high energy. So you would have a partner, and this has a minus sign due to the rule for fermion loops. The contribution of this fermion loop would cancel the bad quadratic contribution from this loop, the gauge boson loop, and therefore then the correction gets tamed. You have only a small scale here, and that's fine. Okay, that doesn't bother you. That's a small correction. So therefore scale scrambling or the gauge hierarchy problem is controlled. And there are non-renormalization theorems that tell you that the parameters of the supersymmetric Lagrangian receive only wave function renormalization and no other coupling constant renormalization. And moreover, we didn't discuss this, but in order to make sense of the grand unification, you see that the standard model couplings G2 and G3, and also G prime, which is this G1 is basically square root 5/3 times G prime. Okay, square root 5/3 times the hypercharged gauge coupling. Now, these are very different in magnitude at the Z boson scale. That their values are known. Alpha strong, for instance, is 0.113 or something, and G2 is much smaller than that. So they are very different from each other. So then how can we talk about, they being, the gauge bosons belonging to the same gauge multiplet? If they belong to the same gauge multiplet, all the gauge couplings must be equal, but they are not equal. So what are we doing? So the answer of that was that, well, you see, this symmetry is broken spontaneously at some large scale, mx, where the sigma 24 gets the wave. And so if you run these, the gauge couplings using the renormalization group equations in the SU5 model with one or more Higgs 5-plets, then you find, or Higgs doublets rather, that means light doublets, you can choose that as a parameter, then you'll find that they approximately unify at about 10 to the power 14 GeV. So in the 1970s, when the data, the low energy data was not known very precisely, sine squared theta W and all, were not very precise, this was sort of satisfactory that, okay, that's the reason why these gauge couplings are so different now, because at the high scale, they're the same and the RG running is different. So when they run down to low energies, G3 becomes big and G2 doesn't become so big, okay? And G1 also is small. So now, you look at the in 1992, this calculation was redone. Actually, it was already done around 1983 by Senjanovic and Marciano, and they predicted that you could get very good unification provided the top quark mass was greater than about 200 GeV. Now in 1992, when the LEP data was already in, then Ugo Amaldi ran the renormalization group equations and showed that for the MSSM, with only one Higgs doublet pair, H and H bar, the three couplings ran together and met at a point which was 10 to the power 16.25 GeV. All three lines converged. You see, two of them intersecting is not a big deal. But if you have three of them intersecting at a point, that, for a physicist, that is really a rat. I mean, that's really a golden horse. That why should they, converge to a point? That makes this idea of their unification much more appealing. That yes, there is a scale, this scale of supersymmetric unification is indeed seems a highly motivated scale. And that has been one of the main motivations driving supersymmetry. We'll see others that come along, but this has been a big deal for a long time, this graph. When you get into actual models, there are messy details, but anyway, this was noted and caused a sensation. So they unify at a point. Non-supersymmetric models do not unify no matter the number of Higgs that you assume. They just don't run together. So non-SUSY guts became much less popular after about the early 90s. Again, the non-discovery of SUSY has made non-SUSY guts again under consideration, but anyway, the thing is open. Now, this is a strong motivation. But of course, experiment tells you that the super partners of the quarks and gauge bosons, that they have to be pretty heavy. So the gauginos have to be greater than about 200 GeV at least, and the quarks and leptons at least 500 GeV, and maybe they have better limits now for LHC. But anyway, they have to be much heavier than the the standard model scale. And supersymmetry, moreover, must be broken explicitly, because if it was broken spontaneously, you would have a Goldstino, and you would have unacceptable sum rules for the splitting of the fermion and the superpartner masses. So therefore, you turns out you can introduce mass terms for the new particles without spoiling the supersymmetry cancellations in the diagrams. And those, so you can write scalar mass terms and gaugino mass terms, and you can still preserve the good. So those are called soft supersymmetry breaking terms, and you can preserve the supersymmetry, hierarchy, solution to the hierarchy problem. Now, the Lagrangian is simplicity itself. It's super Yang-Mills Lagrangian is F squared for the gauge boson, psi bar d slash psi for the fermions interacting with the gauge bosons, and then for their superpartners, which I've called S, you have the similar covariant derivative squared of the scalar squared. You have a new contribution to the potential called the D terms, and then there are the Yukawa contributions. The Yukawa contributions are gotten from a function called the superpotential, which is supremely important, which is a gauge invariant built without taking complex conjugates from the chiral superfield in the model, and it gives you both Yukawa couplings and new quartic couplings between the superpartner scalars. So now, the one very important thing which was noticed very early on by Weinberg is that once you have these new particles, then you can write down new interactions involving the superpartners and the quarks which violate baryon number. So for instance, you write down a superpotential QH D conjugate L. So you see that the baryon number of Q is 1/3 and D conjugate L is, sorry, these are hypercharges that I've written down. But so therefore you have terms, one second, sorry, this is the R parity preserving guy. So these are the normal Yukawa couplings, but there are new couplings which go like this. These are called R parity violating couplings, and they violate baryon number. So for instance, here you have U conjugate. So each one has baryon number minus 1/3. So therefore the baryon number of this operator in the superpotential is -1. And therefore it will lead to processes that can violate baryon number when combined with these other terms here. This one violates lepton number, this one violates also lepton number and not baryon number. So the combination of these two can lead to catastrophic BL violation because this will lead to trilinear scalar terms and so on, with where the term in the Lagrangian will be proportional to the SUSY breaking scale, and you will get bad violation. But if you set these equal to 0 by hand, then non-renormalization theorems guarantee you that nothing bad will happen. Another way of forbidding them is to see that there obviously have to be an odd number of superparticles in these interaction terms. For instance, here I've written a scalar and two fermions, and one of them is a tilde particle, so that's a superpartner. Now you can assign that all the particles of the standard model have R parity +1, they are even, whereas any superparticle has R parity -1. And then automatically terms like this will be forbidden because it has an odd number of such particles. So the new term, so therefore if you impose this symmetry, you will forbid these terms. So, well, that says, oh, that's just something you did by hand. But look, this is amazing thing. They noticed, in fact, Mohapatra noticed this, that you can write R parity as minus to the power of twice the spin of the particle times 3 times B minus L. So then you check that R parity of the quarks is +1 and of the squarks is -1 and so on. And gauge bosons is -1. It's easy to check for all of them, okay? Because the spins of the gauginos are half, so this guy will give you -1 for the gauginos And similarly for the Higgs-Zenos, you'll have odd parity. So it tells you that this very necessary symmetry of the MSSM is a part of the U1 B minus L group. So in models where you gauge B minus L, R parity becomes part of the gauge symmetry. And therefore in the left-right model, the Patisalam model, and therefore also in SO10 model, which includes these models as subgroups, R parity is part of the gauge symmetry. And moreover, it's a discrete guy. So if the gauge symmetry breaks B minus L by 2 units, as we saw that the waves which broke B minus L were even in our left, right and Patisalam model, then R parity is unbroken. And therefore R parity is unbroken down to low energies, which means that you have a stable dark matter candidate. Okay, so this is a very big deal, that supersymmetry provides you a natural candidate for dark matter if there is R parity is a good symmetry. And therefore SO10 based supersymmetric guts provide you a natural candidate for dark matter. Okay, you can also consider Yukawa unification in the supersymmetric standard model, because you have 2 doublets, whereas the electroweak wave is the combination of the square roots of the combination of the squares. Therefore the parameters are not only the wave that breaks the standard model, but also the ratio of the waves of the H and the up and down Higgs, or the H and H bar Higgs. Okay, so V up by V down is a famous parameter called tan beta, common to all 2 doublet models. So therefore now the up and down waves are given by V sine beta and cos beta. And therefore when you look at the masses from the Yukawa couplings, the up quark guys are proportional to sine beta and the down quark guys are proportional to cos beta. So you see immediately that although the top quark mass is more than 50 times as large as the bottom quark mass, and even larger than the tau lepton mass, provided tan beta is large so that cos beta is very small, sine beta will be of order 1. The Yukawa couplings for the top quark and the bottom quark can be of the same order of magnitude. Okay, so this you can estimate them, they are something like this. And in fact, when you take a supersymmetric models and plot not only the gauge couplings unify at 10 to the power 16 GeV, but also the Yukawa couplings unify in the 3rd generation. So again, this was done in the early 90s, and this was again a very convincing sort of argument, though its realization later became more complex because you wanted to do it for all 3 generations. But you also have gauge unification as well as, and this is very natural in models in which the 3rd generation masses, for all quarks and leptons, we'll see in SO10, they all in the same Fermi, representation of the gauge group. So they come from the same Yukawa coupling. And this would be very natural, that large tan beta solutions would give you a very nice understanding of the dominant fermion masses in the standard model, which are the 3rd generation masses. The first 2 generations are sort of, they're very light. So therefore they can get corrections from many places. But the 3rd generation guys are fatties. So their masses are, should be coded in at the tree level. So therefore you have gauge and Yukawa. Also in these supersymmetric models, you have these soft scalar masses that we introduced to break supersymmetry, and presumably they're defined at some high scale where the unified model is defined, but their magnitudes are small. So they are of the order of 1 TeV or so, or 10 TeV or so. And now when you run do the renormalization group evolution of them, you find that Higgs squared turns negative at low energies. And therefore, the symmetry breaking of the standard model can also be achieved starting with positive masses. You have you generate negative masses squared, and therefore you break the electroweak symmetry. So this is called electroweak radiative symmetry breaking. Okay, So, SUSY is good. Now, as I said, we had this chain. Standard model lies in the left-right model, lies in the Pathi-Salam model, and the Pathi-Salam model is a maximal subgroup of SO10. In fact, SU4 is isomorphic to SO6 because their Dinkin diagrams are essentially the same. Right? SO series has this tail extending this way, but SO6 is special because this dot doesn't have anything else to connect to. So SO6 is rank 3 and so is SU4. So these two algebras are isomorphic, and SU2L cross SU2R is isomorphic to SO4. So therefore now it's easy to see that SO6 cross SO4 will be a maximal subgroup of SO10. The other maximal subgroup turns out to be SU5 cross U1. And you also, SO10 also has spinor representations, just like the Lorentz group, which is based essentially on SO4. So SO10 is like SO2 times 5. So it turns out, so there are effectively two fundamentals. One is the vector, which is 10-dimensional or 2n dimensional for SO2n. And then there's the spinor, which is 2 to the power 2n dimensions. So for n equal to 5, this will be 32 dimensional. But because there is an analog of gamma 5 for any even dimensional SO2n group, just like there is for 4-dimensional Lorentz group, there's a product of all the gamma matrices. And the eigenvalue of that will split this guy into two chiral representations. So this would become a 32 is equal to a 16 plus a 16 minus, which has opposite eigenvalues under the gamma analog of gamma 5, which I've called gamma F. So this is the product of all the gammas. And in fact, now you need to convert from spin 10 notation to Pathi-Salam notation, which is, this is unitary group, that is a orthogonal group. So therefore you need to do this conversion, and this was done by us actually quite late in the early 2000s. Once you have that in hand, you can work out the details of any of these models. So for instance, the vector breaks up into 6-plet anti-symmetric of SU4 and a bidoublet of SU2L cross SU2R. And the chiral spinor exactly embeds one generation of the Pathi-Salam model in the supersymmetric notation, because the chiral spinor is a 4-2-1 of the Pathi-Salam group plus a 4-bar 1-2. And since if you put particles in the same representation, they have to have the same chirality, you have to use the anti-fields here. So when you have the anti-fields, you have a 4-bar, and 2, of course, is self-conjugate. So therefore, you see that one generation of fermions, including the right-handed quark or new conjugate L, fits very neatly into one irreducible representation of SO10. And that's much nicer, because 5-bar plus 10 in SU5 was broken like the standard model. It was like, why 5-bar plus 10? It's anomaly free. But SO10 doesn't have any anomalies at all anyway. So therefore that is really nice. So you take 3 of these and you can fit all your 3 generations. The 45-plet is the anti-symmetric representation. So this ij run over 10 values. So 10 times 9 divided by 2 is 45. And you can split it up under the Pathi-Salam group, which I have given by round brackets here. So, well, actually I seem to have changed my notation halfway. So round brackets, so these should be round brackets, okay. So you see that you have, oh, the round brackets were SO6, okay, sorry. These are SO6 cross, okay, I'm talking so fast, should catch my breath, okay. So I want to finish this. It's pretty painful for everybody, I guess, but okay. So these are the SO6 cross SO4 breakup, and then you translate it into SU4 cross SU2 cross SU2. So therefore you have this guy, we needed, these guys were the gauge bosons of the Pathi-Salam model, this fellow and this fellow and this one, and you have new leptoquarks. 622, which actually contain those SU5 leptoclocks plus some extra ones. Because after all, SU5 is a subgroup of, SU5 plus U1 is also a subgroup of SO10. Then you have the 3-index anti-symmetric, which is 120 dimensional. And it also, you can look at the breakup, and inside the breakup of the 3, you have 2 guys which are of interest. You have a bidoublet and a 15-2-2, which was like the sigma that we used to get n goes to pi plus e minus in the Pathi-Salam model, okay? Then you have a 210 plet, which is very interesting because it contains the multiplets that you need for breaking the Pathi-Salam model. So it contains a Pathi-Salam singlet, and it also contains, you know, something that breaks SU4 and also breaks the right-handed symmetry. So it has 3 neutral fields which can be given webs. The rest of them are charged, so therefore these are colored, and therefore, well, charged and colored. So these guys can be given webs and can be used to break down the SO10 group. And finally, there's a very interesting pair of representations called self-conjugate and anti-self-conjugate representations, where you have 5 of these indices which are anti-symmetrized. And if you count, you'll see that this is 252 dimensional. However, SO10 has an invariant tensor which is a 10-index epsilon, and therefore you can split these 252 dimensional guy into a 126 and a 126 bar. And these 126 bar turns out to contain a bidoublet as well as the delta R and delta L that we needed in the Pathi-Salam model. So therefore the type 1 and type 2 seesaws and the fermion-Yukawa couplings can all be neatly accommodated inside the representations that I've told you, and those are the only ones that, apart from maybe the symmetric 54, that most people ever use. So you can, the fermion-Yukawa couplings are extremely neat. So if you take 16 times 16, you get 10 plus 120 plus 126. So therefore only 10 and 20, these are real. 126 bar is complex. So there is the renormalizable fermion couplings are extremely simple. You couple 2 16s either to a 10 plet or to a 126 bar plet. And here the Yukawa couplings are symmetric in the generation index because of the properties of these invariants. These gamma i's are the gamma matrices for SO10. And this B is the analog of the charge conjugation matrix for SO10. And you can make invariants like this. They are anti-symmetrized here, so they can couple to the sigma bar. You cannot couple 16-16 to a 126 because that is not a singlet. So in fact, it turns out to be identically 0 by using the self-duality property. You can also couple 2 16s to this anti-symmetric 3-index guy. So it means that there are only 3 Yukawa couplings that can give rise to SO10 fermion masses in SO10. So these give you all kinds of interesting relations among mass relations. So now there are 2 schools of SO10. This is a slide I always show, and I have 15 minutes. I hope I'll be able to run through what I have to say. So the kind of models that I work on, these are called renormalizable SO10 models. Then there is a class, a very large class of models called non-renormalizable SO10 models. So as the name implies, these do not use any non-renormalizable couplings. Here there are infinite number of possible operators you can write, and basically you write the ones you like and forget about the rest. In order to make sense of what you're doing, then you need ad hoc symmetries for the non-renormalizable guts, but here you don't allow yourself to invoke any ad hoc symmetries. In this kind of model, you use only a few large representations, but you, in the other one, you try to stick with only small representations so that it is asymptotically free. if you count the number of parameters required for this kind of gut, renormalizable gut, to fit all the standard model and neutrino oscillation and so on data, you find that the number of parameters required in this kind of model is much less than, well, these are unlimited. So this is by definition much less than that. But even SU5, supersymmetric and so on have more parameters than these kinds of SO10 models. Here you don't ever duplicate Higgs, you just use one copy of everything. These kinds of models typically take many copies of Higgs model. The R parity or matter parity is a part of the gauge group. Here you have to put in some ad hoc Z2 symmetry to get dark matter and so on. Higgs and matter are very different things here. On the other hand, in such models, Higgs and matter typically mix. You only have B minus L waves because you use these large guys which have B minus L neutral fields. So therefore you only have B minus L even. So R parity is a good symmetry at low energies. Here R parity is broken. And there are basically two such models. One of them is based on 210 plus 126 plus 126 bar, which was written down by Mohapatra and myself and Clark, Kuo and Nakagawa in 1982. And there's another model based on 54 plus 45 plus 126 plus 126 bar, which we wrote down in, I think 2001 or so. So these are the two models of this type. There are billions of models of that type, and I am obviously not in favor of those kinds of models which invoke string theory and so on and so forth, but they have no logic, in my opinion, to them. Okay, so this is the minimal supersymmetric SO10, which is based upon these guys. So it offers you complete, viable, minimal unification. You can break SO10 in one step to the standard model. In fact, you have to break it in one step because with these large Higgs representations, you get a lot of pseudo Goldstone multiplets. And the only way is that they should have a mass of the order of the grand unification scale that we already discovered in 1982. And you have large right-handed neutrino masses. You can break B minus L and R at the large scale. And you have MSSM SUSY gauge unification at 10 to the power 16 GeV. There's one fine tuning in the Higgs sector, which keeps a pair of Higgs doublets light. Everything else is heavy. You can write down a superpotential, which obviously I don't have time to discuss, but it has, the point is that I've written it down here. Then I can count. Okay, there are two versions of this minimal supersymmetric gut. One, you don't keep the 120 plate. The other one, you keep the 120 plate, which is called the next to minimal supersymmetric gut. So the point is that if you don't have the 120 plate, you can count there are precisely 26 total hard parameters in the model, apart from the soft SUSY breaking parameter. That is, may seem like a lot to you, but it is roughly the same as the standard model. Therefore, you have a hope of actually, using, and the number of Yukawa couplings is actually less than the standard model. And so now you can fit the standard model data. So this theory is the minimal predictive theory of quark, lepton, and neutrino or mass data and mixing data. And it, in fact, predicted SO10 that there would be a large leptonic mixing angle, which was actually discovered. However, without the 120 plate, it fails on the neutrino masses. And I showed that sometime in 2005. But if you include the 120 plate, then the original theory that we wrote down in 1982, that guy can fit everything. It has some extra parameters. But even with these extra parameters, which is about 40 parameters, it is still better than the minimal supersymmetric SU5 model. So it is still the minimal model out of all the renormalizable models that we have. It is the minimal parameter counting minimal model. So this kind of grand unified theory is renormalizable, complete, calculable, predictive, supersymmetric gauge theory of everything. It includes the standard model gauges, gauge unification, masses, mixing data, neutrino oscillation data with type 1 and type 2 seesaw. With a proton, dimension 5 proton decay has been bounded by an interesting new mechanism to be greater than 10 to the power 33 years. This was always a problem for SUSY theories, and we have solved that. And it also incorporates inflation based upon the seesaw mechanism. Everything is included. So it's a complete predictive theory. Okay, of course, it involves high scales. So but there's a big elephant in the room, and that was already indicated to you in this table, that this kind of theory, because of the large representations, is not asymptotically free. And people are so addicted to asymptotic freedom that this is a no-go for them. They say, oh, but your theory is not asymptotically free. So therefore, the point of the paper that I've spent all my time not discussing, that I want to justify, is that, you see, the gauge coupling for SO10 of this type of model flows very fast to a Landau pole in the UV above MX. So the beta functions for SO10 couplings, if you calculate them at one loop, the gauge beta function is the index for the representation that you use, the irreducible representations, which are super multiplets, and a gauge contribution. If this is not there, of course, it would be asymptotically free. But then the S2 for all these representations that you use, these are all used as chiral multiplets. These are huge. So for the MS gut, you get 109. For NMS gut, you get 137, which means the thing is asymptotically strong. Okay, so you see how it works. The beta function, dg by dt, where t is the logarithm of the renormalization scale, is g cubed. You can immediately integrate that and get that g squared at any scale is g squared at the fiducial scale, where you define the g squared divided by 1 minus this b0, g0 squared, this is g0, okay? This is g0, log mu by mu0. So it evolves logarithmically, but it changes. So if b0 is greater than 0, then for mu less than mu0, you would get a pole. You would get a Landau pole, right? So this is what happens in the usual asymptotically free theory. So this is the asymptotically free case. So you get a Landau pole at low energy, and the scale where you get the Landau pole is called it's the analog of the QCD scale. So this is Yang-Mills or QCD. And this happens at some small scale of the order of 2.2 GeV or something in QCD. And in supersymmetric theories, because of this large gauge coupling, you expect gaugino condensates, which are the only kind of condensate allowed by supersymmetry. The condensates that appear in QCD, which are FF condensates, cost energy, whereas supersymmetry requires the vacuum to be at zero energy. So therefore you have only these gaugino condensates which don't disturb that, and therefore you have a gaugino condensate that develops. If this B0 is greater than 0, then you have an asymptotically strong theory, and that is what happens in this kind of gut. So now you'll have a Landau pole in the ultraviolet, and at a scale which is just above the perturbative unification scale. So in fact it looks like this. You unified the three couplings at mx, but a little bit above mx, this coupling blew up. And this is what people don't like. They say, well, this guy will contaminate this, and therefore you'll be in trouble. So either you accept that you did all this work, you fitted all the data, it was completely successful from anything you have any hope of measuring. You have included all BSM data that you can think of. And then some guy says, no, but I only believe in asymptotically free theory. Or else you say, well, that means this theory, like in all good physics, is telling me something, that I'm successful, please take me seriously. I'm telling you something, please try to understand that. And that means that this behavior signals that there should be some dynamics that is happening here, which leads to a way, supersymmetric dynamics, which is connected with the gut's spontaneous symmetry breaking. So something is happening here which will lead to webs which breaks the grand unified symmetry. Now, the point is, you might say that, well, okay, but it's all non-perturbative. How will you ever calculate? Now, here's where the magic comes in. This kind of theory is the only theory that you have where you can rigorously say that supersymmetry will be exact. it will be true to 1 part in 10 to the power 13. So you can completely neglect non-supersymmetric effects as far as the dynamics here goes. Where SUSY theories are normally used, strong coupling SUSY theories, the SUSY has no chance of being exact at low energy. So it's an academic exercise. Now, in 1982, Veneziano and Yankelovich showed that this Gaugino condensate develops, and at this infrared condensation scale lambda cube. And after that, there was a decade of strong development of these ideas, which is called cybergistics, which proved a number of very strong theorems which allow you to analyze the strong coupling behavior of supersymmetric theories. And because of the addiction to the asymptotically free paradigm, all the models that this was applied to were asymptotically free by almost by 99.9%. Nobody takes the other guy seriously, but I have a very good reason to take it seriously. So what I did was, I've taken these kinds of techniques and applied them to the supersymmetric grand unified theory, which is asymptotically strong. And the basic idea is to use these techniques to investigate whether Gaugino condensate of SO10 can lead to expectation values of the adjoint type multiplets and break the gut symmetry down to the standard model symmetry or the low energy symmetry. Now I can say more. I'm already at 6:13 now. Please tell me, you want to, I can finish the whole thing in about 10 transparencies. I can give another seminar, or you can be satisfied with what I've told you. Are there any people left here? Hello?
Hello, yes.
Yeah, we are here.
Okay, you haven't run away. Okay, I've been talking non-stop because I saw that people were a little impatient last time. So, I mean, Patta wanted to hear everything in one go. And you see that even the 2 seminars, it took me just to explain in a hurry the background. And without knowing that background, you would not, you would think this is some kind of crazy theoretical exercise in field theory, but it is extremely well motivated. Yeah, hello? So can I have another 10 minutes and I'll wrap up, and if there's any interest, then I can go into the details of the paper some other day. But otherwise we can consider that we have got the main idea has been communicated. So the main idea is that there's a successful supersymmetric gut.
Maybe we finish this, 10 more minutes maybe.
Yes, I can finish that. So I'll tell you the basic idea. Basic idea then is that a Gaugino condensate develops at strong coupling, and that Gaugino condensate drives the spontaneous symmetry breaking. So the technique you use is called the generalized Konishi anomaly. Now the Konishi anomaly is the superfield generalization of the global chiral anomaly, which you're all familiar with, that when you have a chiral current, then its divergence actually has an anomalous term inside it. So recall that if you have a theory with a mass term and you have a Dirac fermion which is coupled to a gauge field, and except for the mass term, this thing is invariant under a chiral transformation, global chiral transformation, and which is done with a generator TA, which is, you can take this psi to be a reducible, you can put all your fermions in one column. And then the classical equations of motion tell you that the divergence of this axial current, okay, this axial current is given by the, this term proportional to the mass. So, because this has to be there because the mass term violates the symmetry. If the mass is 0, then the axial current is classically conserved. Now, in quantum field theory, as you may have all heard, there is a quantum Adler-Bell-Jacobi anomaly, and that anomaly violates this. So that in addition to that mass term, you will get another term which is proportional to FF dual. Okay? So this is called the ABG anomaly, and since in supersymmetric gauge theories, everything is built on chiral multiplets which include these chiral fermions, therefore in such theories also we can consider transformations in which we scale only the chiral multiplet or only this chiral fermion, and there will be a chiral current for these chiral fermion, and that chiral current will have an anomaly. Now, because you're in a supersymmetric theory, everything happens in supermultiplets. So there will be a supermultiplet that contains this chiral current, and that is called the Konishi current. That Konishi current is formulated in terms of the chiral superfield and the vector gauge superfield in this way. And if there's a super derivative with respect to the fermionic coordinates in superspace and the ordinary derivative, this is just a way of writing d mu. You convert it with using sigma mu. And the chiral superfields are functions only of the combination of x and theta, theta bar. Okay, so they have fields of one chirality and they are annihilated by the anti-covariant derivative, d bar, super derivative. Okay, so if you in fact form this guy, d bar commutator on this Konishi current, then you'll find that the lowest component of that of this current is in fact the J mu phi. And because you're in a super thing, there's also a scalar contribution. Now, the Konishi anomaly generalizes the ABJ anomaly. So what it looks like is that d bar squared on this Konishi supercurrent is equal to the terms that violate it classically, plus another term, and this guy basically includes the gauge chiral superfield. So this guy is made from that vector superfield and contains the gaugino, the d scalar, and the gauge field strength as its, this is no theta, 1 theta, and this one is also 1 theta, apparently, components. Okay. So this guy, this W alpha is the guy that contains the gauginos, and you see that this divergence, this is proportional to the gaugino squared operator. So in a SUSY vacuum, the vacuum expectation value of this operator has to be 0, and therefore you get a relation between this invariant and this invariant, between their vacuum expectation value. So in SUSY vacuum, d bar squared is 0. So this guy, for just one chosen chiral superfield, is expectation value is related to the expectation value of the gauge, of the square of the gauge chiral superfield. And if you look at the lowest theta component of this, then this is all scalars and this is all gauginos, because I showed you that the lowest component has the no theta guy is the gaugino. So therefore, we see that there's a relation between scalar expectation values and gaugino condensates. So now what Cacciazzo, Douglas, and Seiberg did was that they generalized this guy. This was derived by taking the variation of phi I to be proportional to phi I. That means it was phi I prime was e to the power of I alpha I phi I. Okay, only one superfield was given a phase. Now that led to a conservation law or a broken conservation law. Now Cacciazzo, Douglas, and Seiberg realized that if you look at the proof of this anomaly, specifically the Fujikawa proof, then you can show that you can take arbitrary variations, which are chiral superfields, in the same representation as this chiral superfield, but are functions of phi and of the gauge chiral superfield. And then you get the generalized Konishi anomaly, which looks like this, that you take a variation which is a function in that representation, and you contract it by the derivative of the superpotential with respect to the superfield that you're talking about. And that is given by the expectation value of the gauge chiral superfield times some extra stuff, which involves this variation. See, in the Konishi anomaly, Fi was phi itself. So d by d phi of Fi was just 1. And these were just the gauge generators. Now you have something extra. So you have a whole infinite series of of relations because this Fi is arbitrary. Okay. I don't know, somehow yeah, okay. So here, so what they did was that they collected, okay, one second. So these MAs are the generators of the gauge group, and the original derivation that was given was for the gauge group UN, and phi was in the n cross n bar traceful adjoint. So now this transforms as U phi U dagger. So the superpotential is given by trace of powers of phi. Now there's a something called the chiral ring, which is you consider all possible powers of phi traced. These are gauge invariant, and all possible powers of phi times one product of WW. And these we'll call Tn and Rn, and these are all the possible members of this chiral ring. And it turns out you can show that the vacuum expectation values in a SUSY vacuum they are gauge invariant, obviously. They are also position independent waves. So, so therefore, what they did was they collected these guys, these operators, into one operator, which was given by using resolvents. Okay, so you take WW divide by Z minus phi. You can divide because phi is a matrix, so you can divide sensibly. And similarly, you divide not 1 divided by Z minus phi. If you take the expansion at large Z, then the coefficients will be precisely Rn and Tn that we considered over here. So now what they did was, if you take delta phi as proportional to this guy, W divided by Z minus phi, you get from the generalized Konishi anomaly an equation for this resolvent which contains all these generators of the chiral ring, which you can solve immediately in terms of the superpotential as a function of Z. That means you take the superpotential and replace phi by Z. And it defines this quantity, which is the quantum superpotential. You see, there's a derivative of the superpotential, and rather the derivative of, it's a quantum superpotential derivative. So this F contains the quantum effects. So if this F is 0, then of course you come back, Rz is equal to 0, and you don't have any condensates. So Y squared, this is the kind of equation you see in Riemann surface theory. So this is the holomorphic function of Z, and if W is cubic, then this is quartic, and Y is therefore square root of a quartic. Okay, and this F is a function whose values are determined by the first two condensates. First one is the Gaugino condensate, is the Gaugino condensate. And the second one is the condensate of WW times phi. So these two condensates will drive all the other condensates Rn for n greater than 2 or equal to 2. So if you do the Konishi anomaly with no W in the variation of phi, you get another equation for Tz, which you can solve in terms of this quantum superpotential derivative. So in this way, you can solve for all the guys that are not in these two integration constants, Cz and Fz. So this gives you a magical way of finding the Gaugino condensate, of finding all the condensates in the theorem. Now, Seiberg gave an extension where he added also fundamental and anti-fundamental fields, which you can call quarks if you like. And these allow you to, their webs will allow you to reduce the rank of the group, which adjoint type webs never allow you, because the diagonal elements are always neutral under the maximal subgroup. So therefore they are neutral with respect to the diagonal generators. But these guys can allow you to reduce the rank. And Nakulich, Schnitzer and Willard also extended it to symmetric representation. Okay. And their couplings of these guys to phi are very natural. So you will have phi I, ij, qj. And similarly for these guys, you can also write the thing. So these are all in sort of matrix form. This is a vector, dagger, matrix, vector, and this is also the trace, a matrix trace, because sigma and sigma bar can also be considered matrices. So you can do a lot of the same tricks also with these representations. And this was applied to asymptotically free models, and you got low energy condensates from the generalized Konishi anomaly, which allowed you to solve for all the condensates in the theory. Okay, but there the emphasis was on confinement at low thing. My thing is now what we did is we generalized this model to the case where you replace the fundamental cross the anti-fundamental by any representation of any gauge group G. Okay, and that immediately you'll see that for anything higher than the fundamental, this guy is already asymptotically non-free. And then you can add quark type guys in R and R bar, which I actually don't need, and also use R cross R and R bar cross R bar symmetric. So you can carry over that entire thing which was developed for asymptotically free theories to an infinite set of asymptotically strong theories. Once you've done that, these waves can break gauge rank also, because SO10 is rank 5, so I need to break gauge rank. And we now assume that the condensation in the ultraviolet above the grand unified scale is leading to a gauge condensate, and then this gaugino condensate will lead to waves for phi, sigma, and sigma bar. So you deduce these waves using a new formula based upon the, which was not considered earlier. That is an invention, I think, of mine, or at least something I advocate. So it turns out that the branch points of the quantum superpotential derivative, that is YZ, they define a Riemann surface, and you can extract the vacuum expectation values you want by taking a contour integral around the cycles of that Riemann surface. So this is AI. Okay, the branch points, so this is, are basically, they run between that. So this is basically what I've done, that you can calculate these waves, and the SO10 AS gut model, what you do is you take the base representation to be R, then phi will be 16 cross 16 bar, and you notice it has a singlet, 45 and 210. This was precisely the representation we used in the NMS gut. And actually it's not very convenient to extract out these guys. I mean, it's better to take the whole thing and just do your symmetry breaking. And 16 cross 16 is 10 plus 126. So therefore 16 bar cross 16 bar will contain 126 bar. So therefore sigma bar contains a 126 bar and a 10, which can give rise to fermion masses and so on. And the 3 sets of fermions you can put inside a 16. So this allows you to build a realistic model with dynamically generated waves, even if you put all the mass parameters in the theory to 0. That means you have no scale at all in the theory, but you have a scale which is dynamically generated by renormalization group evolution of the SO10 coupling. So the Landau pole scale will set the vacuum expectation values in your theory. So therefore, that's what is called dimensional transmutation, that you start with a dimensionless gauge coupling and you generate a dimension full scale. So without any input masses, you will generate you just tell me the unification gauge coupling and I will generate the scales in the theory for you. So this is basically the idea of the thing, and in case anybody is interested, I can at a later date discuss with that person. Okay. So I'll stop there.
Okay, so very good. If there are no immediate questions, I think we should wind up. It's already 6:30.
Yeah.
Any questions?
One question. I have one quick question.
Okay.
Yeah, Mr. Aulakh, see this neutron anti-neutron oscillation that is giving rise to BL delta BL as a 2. There is 2 level symmetry. I mean violation, violation. So the experiment, if experimentally it is found, is that mean the universe would have the mass only matter, not antimatter, or the spiral can also wash out the signal? How do we separate them?
No, I mean, I don't think there's any connection there. That is, if you find it, it means that there are particles, leptoquarks that can mediate it. That doesn't mean that there is no leptogenesis or anything like that. There's no exclusion like that. And in any way, experimentalists take an agnostic point of view as to the theory that gives rise to it. Once you tell them the NN bar oscillation is there, then obviously by definition it is delta B equal to 2 process, but that doesn't mean that there are no delta B equal to 1 processes or processes that obey other selection rules.
Delta P equal to 1 process would be the decay processes. For example, proton decay would be that way it can give it.
Yes. You're right. So proton decay would be there, but for instance, in leptogenesis, first you generate the lepton number by decays of Majorana neutrinos. And then the anomaly, which actually I prepared something for you guys, I didn't have time to talk about it. I did include there were some questions last time. And,
only thing I see that this neutron anti-neutron oscillation would be intermediate energy. It will be much less than that of Earth scale. So
yeah. Otherwise, it would be completely unobservable because it's suppressed by the 5th power of the scale. The operators are suppressed by 5 powers of the scale. So therefore, anytime, whereas the gut amplitude is suppressed by only 2 powers of mx. So mx has to be very large for that reason, because you know that proton decay lifetime is very large. Whereas NN bar is not easy to investigate so easily. So the limits are much lower. The tau is about 10 to the power 9 seconds, I think. And
9 second 3. Sorry, no. Yeah. That violation oscillation will be 10 to the power 9 or 10, something like that.
Yeah. So that's the European spallation. Laboratory aims to carry that forward a bit. And it's obviously very interesting, but that will probe scales that are much less than the grand unified scale.
Yeah, true. But the free neutron oscillation would be much, it would have been found by now, I think.
Why?
Because free neutron, the decay time of neutron is 13 minutes. So in free neutron particularly. So, or if it is like bound neutron, then
but
bound
10 to the power 9 seconds is enormous, no? That means you'll have to watch a whole large number of free neutrons for 10 to the power 9 seconds.
So if I take cold neutron of 10 to the power 10 numbers, which is now.
So say you have a beam of 10 to the power 10 cold neutrons in a beam.
Yeah, that is
and,
not.
You watch it for some seconds. Then you will have to detect the conversion of one of those guys. So I guess you would expect to see some kind of, gamma ray flashes or something from the annihilation of N and N bar.
Yes, true. But in
therefore, this European spallation source, which takes these neutrons, which are, low energy guys, presumably tries to do those kinds of checks also.
Their luminosity is not that high, so they do not get 10 to the power 10 neutron in a beam, because you need some to isolate for gamma. You need that kind of annihilation gamma. You need to have a very isolated environment. So in that sense, you have to have a very cold beam. But otherwise, let's say if it is bound state, then we should see everywhere, because all nucleus will become unstable. If it is neutron anti-neutron annihilation, then it becomes unstable, right? Isn't so?
I don't know. I mean, this is all I can tell you is that they have considered that, and the limits are about 10 to the power. I mean, it's a messy environment also. So I don't know. They have to. I can't tell you.
Yeah. Okay. So
all I know is that the limits are about 10 to the power 9 seconds.
Yes.
And I think that applies to bound as well as free.
Yeah, so connected quick question, why not the proton anti-proton oscillation? It can also happen.
Oh,
There are
that violates charge. That violates charge.
okay. So this is the only channel, the neutron anti-neutron. Yeah.
Yeah, for delta B equal to 2, that's the most obvious one. I guess maybe you could cook up some process.
I think lambda anti-lambda can also give, because that
Yeah,
doesn't.
yeah. No, of course, sorry. Yeah, but those guys are such short lifetimes, most of them. You need something that will live for some time, right?
Yes.
Lambdas, even when you inject them into nuclei and all, they don't live very long.
It is 10 to the some minus 6, 7, or very, very short.
Even if they are decay only weekly, they have at least, some picosecond kind of lifetime.
Yeah. Okay.
Yeah.
And thanks.
So these neutron anti-neutron oscillations, there have also been lattice studies. People have studied this on the lattice. So there is this group at Livermore Lab, Lawrence Livermore Laboratory. So they are pioneering this the work on the lattice.
Yeah, it's very exciting that such a thing. So did they find some?
I don't know. I don't know the current status.
But
They're trying to put some limits.
They need some source. They need some source of baryon violation. What is their source of baryon?
This is a numerical simulations. It's lattice simulations.
I know, but they have to put something into the Lagrangian that will cause it. Is it like a chiral anomaly? Is it a chiral anomaly? Like that was what I was going to show you.
I don't know. I don't know exactly how they do it, but there are papers on this. Yeah.
So I don't know if those guys are here last time. Remember, there were questions about the anomaly-free global symmetry. So if you look at the screen, I've shown you this is the the anomaly equation for the standard model.
Yeah.
And then if you see that in the standard model, the baryon number current has an anomaly. And also, the lepton number has the same anomaly. So B minus L is anomaly free. And if you now check so this was a question that was asked last time. So I had these transparencies somewhere, or I wrote them. And yeah.
I have similar question, whether it is a local or global symmetry.
What?
I mean the neutron anti-neutron violation, or this VL, what you say?
Well, the source of that, the diagram I showed you, was due to the spontaneous breaking, basically, right? Can I show you the diagram?
So then it's
again,
local symmetry, right?
Well, the web that was broken was this was the one, right?
Yes.
Yeah, here. So you see, you have these deltas, and then there's a delta wave. The delta wave that gets a wave is actually delta L, thing. But then it gets converted by these interactions into something that violates baryon number. Because delta R, remember, the thing that gets a wave, this thing is a color neutral guy. So this thing is something like T3L equal to 0, T3R equal to -1, and maybe TB minus L is equal to 2. So it's the charge is 0. So the thing that is getting a wave is, and of course it's color neutral also, is basically a guy with lepton number. But because of the structure of the couplings, it lands up in an operator where you have 6 quarks.
Yes.
Because the theory has B minus L symmetry, so it can do that. You can trade the L for the B. And in the end, you have this delta B equal to 2 operator that's come out of a wave, which violated B minus L. So all this stuff is not as trivial as it looks. I mean, there's a lot of work you can do on it. Mohapatra and Robert Schrock, I mean, I remember they're still working on things like this, though they did a lot of work in the 80s. Now, I don't know what Anosh is talking about, it may be due to that when you are simulating the standard model on the lattice, then you would have a chiral anomaly. No? So typically when you take ensembles and you run the ensemble, then I know that Shaposhnikov and people like that used to do that. They see that in the ensemble there are fluctuations which create B and this B minus L current gets, I don't know if you include leptons anyway, but if there's a chiral anomaly, then okay, I wrote that also down somewhere or the other, but that, you see that chiral, one second. So if I do that, you see if you have d mu, j mu, this is equal to dt j0. So equal to 0 or equal to x, let's say, then this will be d0 j0 is equal to div j minus plus x. So therefore, if you integrate this over time, right, from minus infinity to infinity of j0, then you will get q infinity minus q minus infinity is equal to the integral of x. Okay, so now you see that I mean, you are also integrated maybe your d3x or something. So so the point is that your d3x also. Okay.
So Charan,
So you see that if this was the
I just sent
baryon
you an
number
email.
current, then you would violate baryon number.
So Charan, I have to go.
Okay.
There is a, I had to,
Yeah,
there is
it's
a
okay.
delivery.
It's fine. I just wanted to tell you that your baryon violation could be connected to the standard model.
So I just sent you the link to the paper, the archive link. So that
Okay.
will be useful. So I think we should wind up now. So
Okay.
Yeah. Thank you so much, Professor Aulakh, for a nice set of lectures. So next week we'll meet for the next meeting.
So actually, you should let Anosh
Thank you.
go. But the students, I just want to know. I mean, what is the? I'm really puzzled. This new medium. I can't look at your faces. I can't see how baffled or how interested you are. So it's really a difficult format. So did you guys manage to get anything out of this quick recitation, or is it not interesting? I mean, we have to know, unless you make some effort to communicate your feelings, some serious damage is being done to the academics. How many people do we have here still? There's how many people? Eight participants. Who all are there? Amresh, Arpit, how much of this stuff can you understand? Minati Biswal and Vamika Longia. Okay, so only 3 students. So I don't know. I mean, the journal club has to think also, right? That how much is being communicated. I don't know. I really would like to know. I wish feedback.
Sir, I have a question which I
Yes.
wanted to ask. So so this asymptotically strong nature is in MS guts is coming from the spontaneous symmetry breaking after the unification.
No. The asymptotically strong nature comes from the fact that you have a lot of fields.
Okay.
You see, you have sigma 210, you have phi 210. So that's 210 chiral multiplets. Each one contributes something. So I showed you I showed you the B0, where is that? It comes from the fact that the, so it comes from the fact that, here, the next guy is here. You see here, the beta function tells you how the gauge coupling changes. And the beta function is given by the index of the representation minus thrice the index of the adjoint representation. That's the quadratic Casimir invariant. And the numbers here here the dimensions and the indices of the different representations are given. So for SO10, the adjoint has an index 8. So this would be minus 24. So if the SR was less than 24, then this theory would be asymptotically free. So if you use only small representations, 10 and 16, then you have no problem because you've got 24 there. As soon as you start doing things like putting in 120, 126, 126 bar and 210, you have huge guys, much bigger than 24. So it's gone. Asymptotic freedom you lost as soon as you start using a large representation model. So then you'll say, naturally, why? Then you shouldn't use it. But the trouble is that if you use small representations, then the constraints of symmetry and your ability to do things like generate neutrino masses and preserve R parity and all, any 16 type Higgs will destroy R parity. That is all gone. So all the desirable things also go out of the window. So if you keep the desirable features, then you are being driven by the phenomenology into considering these large representations. And if you do that, you build a very nice model, then the gauge beta function is positive, and then this running immediately tells you that it is for mu bigger than mu0 that you will have the Landau pole, not for mu smaller than mu0. So at the unification scale, perturbative unification scale, where the gauge couplings run together, the gauge coupling is small. But as soon as you start evolving beyond that, when the heavy particles, you see the heavy particles have large masses. So most of these large multiplets, the particles are heavy. What survives in the low energy theory is only the MSSM. That is the crucial thing to understand about guts. That you have all this structure at high energies, but it's not visible at low energies, except indirectly. So did I answer your question?
Yes, sir. Thank you, sir. Okay, so one follow-up question, like, does the superpotential nature or the parameters also come into play here?
Yes, yes, you can in fact write down the renormalization group equations for all the parameters, not only the gauge, and you can do it up to 2 loops or 3 loops or whatever you like. And we've done that actually up to 2 loops. For SO10, we've written down the RG equations. We have a paper published in PhysRev-D, I think. It's quite a complicated calculation, but certainly you could consider also the contributions of those guys in the ultraviolet. But basically, when you have 109 and 137, there's no way to stop the thing from blowing up. That's such a huge beta function. There's no way that you would be able to avoid the gauge coupling blowing up.
Okay, thank you, sir.
Which is, as I say, not necessarily a bad thing. The theory is telling you something. And, you know, I mean, if you want to listen, you listen. Okay, so should we stop?
Yeah, yeah, we should stop then. Thank you, Prof.